Okay, so we're at class 4. Class 4, we're going to talk about 2.2 today. So you've had 3 homeworks thus far. You submit homework and questions of the day through your folder. So whenever you're handing something in, you just put it in your folder. And the things that I've been collecting are the homework problems that are, the homework assignment is listed at the end of each class, and the questions of the day, right? So if we go back in the syllabus, you can see if you're doing test heavy, you wouldn't need to hand any of them in, but for either of the other 2 options, questions of the day and homework both have a percentage attached to them. So questions of the day are also at the end of each lecture. Come on. So like if I go to the end of yesterday, this learning objectives for class number 3, there's a homework assignment. And then a little bit later, there's 3 questions of the day. So they're questions about the reading for the next class to help you prepare for the next class. So I've just noticed that I've seen some people doing just one or just the other. And if you're doing test heavy, like I said, it doesn't matter. But just know that both of those things are graded. I will accept homework up to a week late, so you still can hand in some of the old things. Yes, same thing with questions of the day, yeah. I'll take those up to a week late as well. And then after I grade homework, I put it back in your folder with a check mark on it, and you can take it out of the folder and put it back in your notebook at that point. Okay, so projects should be well underway. You have a timeline for each project. You should be like about, I think it's at about number 3 on both of them. There's going to be a little lag at this point because you need some calculus to finish, to move on with some of these projects, and we don't have everything we need yet. So I'm going to open this one up. So this is the arbitrating disputes project. Take a quick look at the timeline. So by class 6, you should have completed the supplemental exercise. There's some serious reading attached to this, right? The supplemental exercise that takes some effort to digest. So that's why you have a couple of classes to do that. And then not until class 8 can you get to number 4. Okay, so number 4 requires a little bit of calculus. So that's not going to happen for a little while. But just because the problems don't require calculus doesn't mean they're not hard, right? So you might want to make sure that you're on top of that. Okay, so today we're going to talk about the derivative at a point. This is section 2.2 in your text. We're going to define the derivative as the slope of a tangent line and also extend our instantaneous velocity to a more general instantaneous rate of change. Okay. So everything that we've done with velocities over the last few classes, average velocity being a secant, slope of a secant line, instantaneous velocity, the slope of a tangent line, we can apply all of those concepts to arbitrary functions, not just height or distance functions, so that we're not just talking about distance and speed. So for a general function, average velocity, instead of saying average velocity, we start saying average rate of change. If it represents anything other than distance and time. We talk about average rate of change, and instant velocity becomes instantaneous rate of change. So the instantaneous rate of change, right, we defined this instantaneous velocity earlier, so now we're just going to say instantaneous rate of change. For a function f of t at a point A, so t equals some number a, it could be like 5 or 18 or whatever, is given by this limit. So f of a plus h minus f of a all over h, and then let h get really, really small. Take the limit as h goes to 0. Okay, so Just so we can refresh our memories, what does this h represent in this formula? A small number. Yep, it's a small number, and it's a small distance change in time when it was a distance time graph. Now it's going to be just a small change in x if we're talking about a general function.
Could be notated as delta x.
Delta x, sure. Or actually delta t, because I defined this with t's, but yeah. So yeah, let me just draw a little picture. We've seen this picture before, but just to remind ourselves, here's some arbitrary function. If I want to know the instantaneous rate of change at a point, let's do right here, we'll say A. Okay, so this point on the graph has coordinates A, comma, f of A. Right, f of A is just another word or symbol for the y coordinate at A. And then I'm going to go some small distance to the right of A, and I'm going to call that distance that I move to the right h. This is the distance h, which means that this point right here is A plus h. So this point on my graph is A plus h, comma, f of A plus h. Okay, so far? So now I'm going to connect these 2 points with a secant line, and the slope of that line is the change in y over the change in x. So I would do f of A plus h minus f of A all over A plus h minus A, which is h. My change in x is just h, that distance along the x values. So that's the slope of the secant line. If I want the slope of the tangent line at A, I just let the h value tend towards 0. I let it get smaller and smaller and smaller. And then this secant line, this point is like sliding along the curve, and the secant line will approach a tangent line at A. So my instantaneous, this is my average rate of change. ROC is my typical notation for rate of change. If I want my instantaneous rate of change, I take the limit as h goes to 0 of this expression.
Just go as far as you go, or as far as the required.
To figure out what the limit is?
Figure out.
Yeah. Yep. So you just let h get smaller and smaller and smaller, and usually there's some pattern, like it's approaching something, and that thing that it's approaching, we say, is the limit. All right, so that's just a little review. Let's apply what we know here. We have the population. I'm going to call this f of t instead of p of t, just so we can keep the notation from the definition. F of t. The population of China, we're going to call it f of t, in billions, can be approximated by this exponential growth function, 1.267 times 1.007 to the t, where t is the number of years since the start of 2000. We want to use this model to estimate how fast the population was growing at the start of 2013. And rounding is a really bad idea here. We're not going to round anything. And then we also want to know how fast it was changing at the start of the year 2000. So what t values correspond to the year 2013 and the year 2000? 13 and 0, yeah. So can I just do this? Just plug them in and those will be my answers? That would tell me the size of the population, right? But what are they asking me about? How fast it was growing, right? So the size that it is tells you nothing about how fast it's growing. So these aren't going to help me, right? So instead, I'm trying to find a speed. An instantaneous rate of change is what I'm looking for, an estimate for the instantaneous rate of change. So I'm going to use this definition for instantaneous rate of change. Average rate of change is a good estimate for instantaneous. Okay, but I'm just going to take h to be really small. Take h to be really small. What am I going to use for a? 13 and 0. Those are the points I'm interested in. Okay, so I'm going to do f of 13 plus, what's a small value for h I could use? 0.01, yeah, 1 is a little bit big. Maybe 0.01 or 0.001, something like that. So I just wrote down the definition for average rate of change. I'm going to use a small value of h, which would make it a good approximation for the instantaneous rate of change. All right, so now I'm just going to plug these things into my function f. So I'm going to have 1.267 times 1.007 to the t, which here is going to be 13.01. Right, now I'm plugging in a 13.01. And then I'm going to plug in a 13. All divided by 0.01. So I'm going to type this all in one fell swoop in my calculator because I don't want it to round to anything. Because this is being measured in millions, so even if it's off by only a decimal point, that's 100,000 people, right? So I'm going to not try to round anything and just type this all in at once, so not to introduce any rounding error. Oh, billions, sorry.
Well, it says gigabytes.
Oh, interesting. Okay. So, no, yeah, so we'll just see what the answer comes out to. Maybe it makes sense to answer in millions rather than billions. Okay, so I've got 1.267 times 1.007 raised to the 13.01 minus 1.267 times 1.007 raised to the 13th. And I have that whole numerator in parentheses. And then I want to divide by 0.01. So I get 0.009677. 0.009677. So what are my units on this guy? Billion, just billions? Billions of what? This is a growth rate. This is a rate, so billions of people per year. Yeah, so when I plugged in to my numerator, I was just plugging values into the population function. So my numerator units are billions of people, right? My denominator units, a 0.01, that was a small change in time, right? So that is years. So my units are billions of people per year. So now I can see why they asked us to answer in millions, because it's such a small decimal when you're in billions. So how do I change that to millions? Decimal point 12 though, right? So this is it just 3 to the right? 3 to the right. Yeah, because, yeah, this would be like hundreds of millions, tens of millions, millions. So if I answer this in millions of people per year, I'd have 9.677 million of people per year. So that's really fast. Almost 10 million people per year population of China was growing at in the year 2013. Yeah. The smaller the H value, the better your estimate of the instantaneous rate of change. So, but what is small, right? Because you can always get smaller, right? So whatever the definition of small is we haven't it's not well defined. Yeah. Right. You would come out with a slightly different answer if you'd used 0.001, but this is an estimate, so there is no like exact right answer. Came out pretty much the same. Okay, good. Yep. All right, so I'm going to skip doing the 2001 for now. We'll just move on here. That limit, the limit as h goes to 0 of f of a plus h minus f of a all over h. So we already know it represents instantaneous rate of change. It represents the slope of a tangent line at a, and we call it, it's so important, it has its own name, and we call it the derivative of the function f at the value x equals a. So in general, we use an independent variable of x instead of t. So I might switch back and forth. So to summarize, here's our most important definition of the semester. The derivative of a function f at an x value x equals a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. And there's this notation right here. You read that f prime of a. It means the derivative of f at a. So you read that f prime of a. That's our notation for the derivative. Finding the derivative of a function is also known as differentiating the function. So when you're reading the directions in your homework, they might say find the derivative. They might say differentiate. If a function has a derivative, we say it's differentiable. All of these phrases are important. They'll hopefully become second nature to you soon enough. Okay, so as we've seen, the average rate of change of a function, that's f of a plus h minus f of a all over h, is the slope of a secant line. And as h goes to 0, what does that secant line become? A tangent line. Okay, so I have a little animation that I'm going to show you to have a geometric look at the derivative by playing with some tangent lines. Okay, if you're not here yet, you can tune me out and watch the video later. Okay, so f prime of 2. The definition of f prime of 2 is the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Right? That's just the definition of the derivative of f at x equals 2. So but I have a formula for the function f. I can plug in this 2 plus h and this 2 into my function. So this is the limit as h approaches 0 of 1 over 2 plus h squared minus 1 over 2 squared all over h. Okay, so not yesterday, but Monday, we talked about how to take a limit. How do you find the value of a limit? And you did a whole bunch of problems where you calculated limits. And the thing you want to do is you want to be able to plug that h equals 0 into your function, right? Because the limit is what happens when your function gets really close to h equals 0. Plug in 0.1, 0.01, 0.001. We're interested in the behavior near 0. So if we could figure out what the behavior is at 0, as long as that thing is continuous, we'd know exactly what was happening. But at this point, I can't plug a 0 into this expression. Why not? It'll make my denominator 0, and you can't do that. So I'm going to have to do a ton of algebraic manipulation on this expression, try to get this h that's in the denominator to cancel, and then I'll be able to plug my 0 in. So the algebra I'm going to do is just pretend that this is a problem I gave you last semester, right, when you took pre-calc. Ignore the limit, and I just gave you this ugly fraction thing, and I said simplify it. That's what we got to do. Simplify this thing. So when I look at the numerator, I'm subtracting two fractions. What do you have to be able to add or subtract two fractions? Common denominator. So this one I'm going to multiply by 2 plus h squared over 2 plus h squared. And this one I'm going to multiply by 4 over 4, because that denominator is a 4. Okay, so I've got the limit as h approaches 0 of 4 over 4 times 2 plus h squared minus 2 plus h squared over 4 times 2 plus h squared all over h. All right, so I got a common denominator, the whole purpose of the common denominator, so now I can actually subtract those two fractions. So I have the limit as h goes to 0 of 4 minus 2 plus h squared over the common denominator of 4 times 2 plus h squared. And this is all over h, but instead of doing all this divided by h, dividing by a number is the same thing as multiplying by its reciprocal. So I'm going to write times 1 over h. Okay, equals limit as h goes to 0. I'm going to FOIL that. I'm going to multiply out 2 plus h times 2 plus h and distribute that negative sign. So I'm going to end up with 4 minus, actually maybe I'll distribute the negative sign after. 4 plus 4h plus h squared over, I'm going to multiply those two denominators together, and I have 4h times 2 plus h squared. Distribute the negative sign and combine like terms. I'll do that in one step. So this is going to be 4 minus 4. Right, so I'm going to distribute that negative sign to every term here. And so 4 minus 4, those cancel. Then I'm going to have negative 4h minus h squared all over 4h times 2 plus h squared. My numerator now can be factored. There's an h in both terms. So I'm going to pull an h out, and I'm left with negative 4 minus h all over 4h times 2 plus h squared. So that was a really key step, factoring out that h from the numerator, because now I can cancel an h from the top and the bottom. And now I want to take the limit as h approaches 0 of negative 4 minus h over 2 plus h squared. Now if I try to plug in 0 in the denominator, I do not get a 0. Everything's cool. Plug in 0 for h and I get negative 4 on top, and on the bottom I get 4. What did I do wrong? Oh, there's still a 4 there. So I have 4 times 4, which is 16, which is negative 1/4. So now I know that that is the exact limit. Otherwise, I would just be guessing by plugging in smaller and smaller h's.